What is Monte Carlo? Monte Carlo is a method for approximating things using samples. And the things which usually need approximating in machine learning and statistics are expectations. So our goal when we're doing Monte Carlo is to approximate an expectation. So let's say it's expectation of some arbitrary function, some real valued function, or maybe it's a function taking values in Rn, say, or but let's say it's real valued for now. Function f of a random variable x. So we want to approximate this expectation. And typically the reason why it needs approximating is because this is intractable to compute exactly in an efficient way. So we want to approximate it. And here's the definition. Let's give a sort of formal definition of a Monte Carlo estimator. If x1 up to xn are distributed according to some probability distribution p, and they're IID, independent and identically distributed, then mu hat n, mu for mean or Monte Carlo, is the sample mean, 1 over n times the sum as I goes from 1 to n, of f evaluated at the xi's. So this is a, let me say in quotes, a basic Monte Carlo estimator of the mean, the expected value of f of x. I put a basic Monte Carlo estimator because there's all sorts of variations and other methods for doing sort of similar sort of things, similar sort of variations on Monte Carlo. But this is the most basic standard form of a Monte Carlo estimator. Let me put that in a box. And it's just the simplest possible thing, right? It's just, we drew these samples and we wanted to approximate the mean of the mean of this random variable f of x. And so we approximated it by the sample mean. So this is just the sample mean. That's all there is to it. And now let's think about, so maybe before I want to tell you about some properties of this, some nice little properties. But maybe I should mention first that there are some more general things, or some different types of things that people might refer to as Monte Carlo methods or Monte Carlo approximations. But for us, in machine learning, at least, this is what we mean by a Monte Carlo estimator, or a basic sort of standard Monte Carlo estimator. It's when we're trying to approximate an expectation. Okay, so let's make a few remarks, and let's do them in purple. Remarks. First remark, make a little space. So the expected value of this thing, the expected value of mu hat n, what is the expected value? Well, E is linear, so it moves through. The expected value of E of f of xi is the same because they're identically distributed. And that's just this, the expected value of E of f. Well, maybe I should have said here, so here, this is, I was sort of, maybe I didn't say, this x here, this is where, let's add that to the definition, where x is also distributed according to p. Right, because if x had a completely different distribution, then this might be a kind of silly thing to do. So yeah, so here I meant that x is also distributed according to p. Okay, and so now when we compute this expected value, it moves through, and the expected value of each of these terms is equal to the thing we're trying to estimate, and we get n of them, so 1 over n cancels, and that's just the expected value of f of x, if I can write it clearly. And this is what we call, when this occurs, we call mu hat n an unbiased estimator. If you watch the videos on estimators, we define unbiased estimators, and this says it's an unbiased estimator. Its bias is 0. So on average, it's roughly doing the right thing. So that's one remark. So that's a nice property that we have for a Monte Carlo estimator, a basic Monte Carlo estimator. And here's another nice property. Mu hat n converges in probability, I'll say what that means in a second, to the true mean, the expected value of f of x. And this is, of course, as n is going to infinity. And by this, I mean, let me say what I mean by this convergence in probability. This means that for any epsilon positive, the probability that mu hat n differs from e of f of x by less than epsilon, the probability that it's within epsilon of the correct thing, is converging to 1 as n is going to infinity. That's what it means to say that this is converging in probability, and we write it this way. And this situation, when this occurs, we say that mu hat n is a consistent estimator. So a Monte Carlo estimator is consistent in addition to being unbiased. And that's nice. Always a good thing to have. And what I mean, roughly what this means is that as when n is big, then with high probability, you're going to be close to the true thing. So if you were to do this in practice, if you were to actually draw a bunch of samples from the distribution and compute this estimate, then this is saying that with very high probability, you're going to be close to the correct thing. And a third remark along these lines. So we looked at the mean. Let's look at the variance of this guy, of mu hat n. What is the variance? Let's look at the formula here. The variance of a constant times something is the constant squared times that thing. So we can pull this out. We get 1 over n squared times the variance of the sum. And these are IID. So this is a sum of IID random variables. And in particular, it's a sum of independent random variables. So the variance and the variance of a sum of independent random variables is the sum of the variances, and they're identically distributed. So we get n times the variance of f of x, and that cancels one of the n's in the denominator. So what we get is 1 over n times the variance of f of x. That is the variance of our estimator. And this is a constant, this part here, just a constant. And, so I should have made a, qualifier here. This is assuming, so it's consistent, assuming, so I should have put here, this is assuming, thinking about variances reminded me, we need to assume that the variance of f of x, so that's the variance of f of x, is finite for this consistency property. And so the reason why consistency follows from this is by the weak law of large numbers. Okay, so I should have mentioned that here, that this property 2 only holds under this assumption. And now we have this guy, and as long as this is finite, this is converging to 0 as n goes to infinity. So we have the nice guarantee that not only is it converging in probability to the right thing, well, this is sort of very closely related to this, but this is saying that our error is getting very small. On average, our error is getting very small as n is increasing. So we could write this also the mean squared error of this thing using both 3 and 1. We have the mean squared error by the bias variance decomposition is equal to the bias squared plus the variance. The bias is 0, and the variance is this thing, so this is the mean squared error is 1 over n times the variance of f of x, and of course that's going to 0. So this is saying that the mean squared error, if we were to use the square loss, which would be a natural thing to do, use the square loss for an estimate, for a measure of how good or bad our estimate is, our estimator is. If we use the square loss, then we get the mean squared error, and so our sort of average error is this thing, and it's getting very small as n is going to infinity. So usually what people say, if you this is if you take the square root of this is the standard deviation. That if you take the square root of this, well, same thing. So take the square root of this. That's the standard deviation of your estimator mu hat n. And so since it's usually easier to think in terms of standard deviations, people say that this is converging at a rate of, that's rate, not rato, rate of 1 over square root of n. So sort of the error, the standard deviation of the error is roughly, it's going to 0 at a rate of 1 over the square root of n. And this is not a super speedy rate of convergence. It's not exponential or anything, and the square root slows it down even more. But the nice thing, at least, is that, well, it's going to 0, and also this is regardless of the dimension of x. This is completely independent. This is regardless of the dimension that of the space that this random variable x is taking values in. So x could be, some super high dimensional random vector, and yet if you do this Monte Carlo estimate, then you're still getting the same rate of convergence. And the reason why that's the case, the reason why you can get a good estimate even when the dimension of x is high, is because this f of x is just a one-dimensional quantity. That's what we were assuming, that f of x is a one-dimensional thing, this f of x that we're trying to approximate. And since that's a very small, low-dimensional thing, then it's possible to get a fast rate, or well, a decent rate of convergence, at least, even when x is high-dimensional. Now, one thing to note here is that, okay, yes, we have this rate of convergence, but it might be difficult to know what the actual error is, because it might be very, very difficult to evaluate the variance of f of x. Remember, the whole point of this was that we were trying to approximate the expected value of f of x, and so knowing what the variance of f of x might be even more intractable. And so actually knowing what your error is might be a hard thing to know. And so that can be one disadvantage of Monte Carlo methods. And one last remark is that as a practical matter, one needs to be able to sample efficiently from your distribution, to draw these samples efficiently in order to make this work in practice. Okay, so that's Monte Carlo approximation.